Hi everybody, welcome to the Google Hangout with Nova and NASA, and my name is Rachel Connolly. I'm the Director of Education, actually STEM Education, at WGBH. I was a high school physics and astronomy teacher for many years, and I'm really glad any and all teachers have been able to join us tonight who are interested in do-it-yourself science, and today is a particularly great day for this. We could not have planned it better, although it was quite an accident. There's a lot going on right now with the sun, and if you don't already know, let's fill you in real quick. We have a solar eclipse happening as we speak. This is a live feed from NASA that we're seeing, and some of you might right now be able to see this. This is obviously a slightly safer way to look at the sun. Just so you know, there's a showcase of clips and all of the different links that we're going to use in today's Hangout, all available to you in the showcase right-hand side of your window. So on there you should see the NASA TV link that if you'd like to click it and open it, you can watch this for the remainder of the eclipse and enjoy it. We also have a couple of amazing solar flares and sunspot activity happening right now, and something that's beyond belief. Before, we didn't plan on this when we scheduled this hangout, but today of all days is the largest sunspot in more than 20 years currently facing the Earth. And they've had a series of X-class solar flares that thankfully none of them have been ejected and headed our way. But we have a couple more days of this. So there's a lot to talk about in your class right now about what's happening on the sun. Perhaps it's from an Earth science perspective about how our Earth's magnetic field shields us. Perhaps it's about how a star goes through solar cycles. And anything that you might want to talk about, we have some tools today that we're going to help you bring these headlines from right into your classroom. And I always like to start with why we're here. And this sort of hangout series that we're doing is about the stories in science behind the standards. So let's start with what one we're going to talk about today. I like to call it episode Earth and Space Science 1-1, which essentially is the NGSS performance standard about how we understand the sun and the role of fusion all the way to the release of energy and its impact on the Earth. And so what you'll see at the bottom is some of this evidence includes how the sun's radiation varies due to solar flares like the one we had today and the sunspot cycle. And here to help me talk about this today are some of my colleagues from, and I'm going to unmute them so they can talk in that and introduce themselves. First, I'd like to introduce Ralph. Ralph from Nova. So, Ralph, please say hello and tell people a little bit about yourself.
Hi, everyone. My name is Ralph Bouquet. I am the outreach coordinator for Nova Labs. Basically, I work to sort of look for outreach and partnerships with educators as well as sort of other research institutions that Nova works with to develop and create the labs. So you definitely will hear a lot from me. I also do some webinars as well on some of the labs, and yeah, I'm also working to develop some resources that you teachers can use to supplement and implement the labs in your classrooms.
Great, thanks a lot, Ralph. And we also have Troy joining us from NASA. And Troy is our sort of go-to teacher / solar expert at the moment. And Troy, I know that you've got some great stuff to share, and the sun sort of set you up today. Like you didn't know you were going to be dealing with this.
Oh, we orchestrated all of that from NASA. We made sure this was ready for this hangout today. But thank you for introducing me. Actually, I'm Troy Klein, and I'm the Education Public Outreach Lead for one of NASA's newest missions that's getting ready to launch actually in 2015 on March 12th. And right now we're in the middle of putting together all of our materials and resources to help people be part of that launch as far as a webcast and broadcast and all of that. But before coming to NASA, I thought it was important to share with everybody that I was a teacher for about 11 years, and a couple of the places I taught were interesting. One of them was the Navajo Indian Reservation, where I taught 4th and 5th grade. And after that, I went to Peace Corps for a little while and taught in Chad, Africa, which was a lot of fun. So if there are any Peace Corps volunteers out there, make sure you post a text real quick and let me know, or any return Peace Corps volunteers. And after that, worked in education technology, and here I am today working for NASA, so I'm excited to be here.
Wow, that's great. So just so you know, everybody, we have a Q&A window open so you can ask questions at any time, and we really ask you to do that. Troy is going to come back and talk a little bit more about the big picture of solar activity and everything, but we want to start with some of the headlines because this is what's happening right now. And this amazing series of solar activity that's going on right now, as Troy mentioned, or told me to mention, which is a really good point, the largest sunspot in 20 years is currently facing us, and this is the size of Jupiter. And just to give you sort of a sense of scale, that's 10 Earths can fit across the sunspot. And when you see stories like this, which you might see often, you'll see a flare just leaves the sun and heads our way. One question I've always wanted to answer is how you can bring this right into your classroom and do a little more with it than just say watch a video or look at an image of it. And this is where the HelioViewer tool that is the central portion of the Sun Lab, Nova's Sun Lab, and again, these links are all in your showcase for you, can help you go right to the real data. And I'm entering the Sun Lab into the research lab, and there's a open investigation section that allows you to begin and jump right to what the sun looks like right now. And what I think is amazing is look at this. You can actually see this beautiful sunspot right here. I mean, this is it, and this is pointing at us. This is the size of Jupiter, and not only can you see it here in what we call continuum, which is white light, what it would look like if you could safely look at the sun through a very, very heavy filter. But you can also bring in a range of other satellite imagery, and in this case, turn on what this thing would look like in, I'm trying to turn this on, and sorry about this. I have too much stuff running on my computer, so there you go. You can turn on what this thing would look like in other wavelengths of light, allowing you to explore a range of wavelengths that tell you different types of information about the sun. Because remember, the light that the sun or any star gives off is information about its energy and the temperature and the activity happening on its surface. And so what you're seeing here is when you have these sunspots in high active regions, you also have very high energy X-ray radiation being emitted, and you can see the beautiful solar, the filaments and the magnetic field lines that are emanating from this. When you look at these different, and right here you can really see the magnetic field lines. So this gives you a chance to actually delve into the data behind it from a range of different satellites. Right here I've chosen SDO, which stands for the Solar Dynamic Observatory, but there's also stereo and other satellites you can look at. And the tool enables you to step forward and back in time to watch this emerge. So I'm actually stepping back 6 hours at a time, and as you do, it takes a minute sometimes for it to load. You can watch an event happen over time at your and control the data yourself. But the other thing is you can go back in time and look at other important events that are happening on the sun or things that have happened in the past that you'd like to revisit. And I'd like to show you one that was not that long ago. And Troy, I think you said one of your office mates found this.
That's right. Yeah, his name is Steele Hill, and he works for, he's been working for SDO as one of their graphics people for many years now.
Well, and this is just kind of a really cute, connection that you might want to make. Halloween's coming up, and on October the 8th, and that's really important, and I'll show you why in a minute. On October the 8th, there was a picture of the sun where the active regions sort of gave you the sense that the sun looked like a jack-o'-lantern. You've got, the eyes, the nose, the mouth, and knowing the date enables you to go to the lab and actually choose that date and look at it here through a range of different wavelengths. You can see it here, you can move it around, and even take a movie or a screenshot of it. And I just like to be able to show how you can go from what's happening or something you might see that's an interesting story, and in this case to some eruption on the sun. This is a beautiful filament and flare that happened in 2012, and once I saw this video I had to take a closer look. So I went to the Sun Lab and opened it in, there it is, and you can step through time and watch the flare evolve every 6 hours and see how long these really take, because they look so quick. I mean, when you make these videos, right, you can tell us, Troy, you tend to compress them in time, but these take many, many hours or sometimes days to happen, right?
They sure do, and sometimes you can see them happening within hours, and sometimes minutes. You'll be able to see a change if you keep coming back to the Helio viewer and tools like this. And check every hour. Sometimes these things are uploaded from minutes to hours, and often they'll have a timestamp on the image somewhere that lets you know when the image was taken.
So would you say that, I mean, I just realized that right now we're watching the sunspot emerge.
Yeah.
And it's something that people are tracking because now it's pointing our way.
Yeah. Yeah. Actually, what's interesting about those sunspots is as it's coming around the limb of the sun, which is the outer edge of the sun, as the sun's actually rotating, and that sunspot's moving, if you watch the progress of that sun and every day perhaps have your students come in and take a screenshot of the sunspot as it looks every day at about the same time, you'll notice not only is it moving, but it's really changing from day to day to day. And if you look at the other filters of light, and sometimes you can look through some of the SDO images, you'll sometimes see a halo, what looks like a giant halo of light emanating from the sun, and often that means there has been a coronal mass ejection or a large explosion, and that plasma is on its way to Earth. And you may have already mentioned this already, Rachel, but it only takes the light from the sun to get here. It only takes it about 8 minutes. So we often know that there's a storm or there's a huge coronal mass ejection ejected from the sun within minutes, and then it takes somewhere between 3 and 4 days normally for the rest of the plasma and all the material from the sun and that explosion. If it's in an Earth direction, it takes about 3 or 4 days normally for it to reach us. So we have a little bit of time normally to get ready for some of these events with our satellites and technology.
Great. And Troy, that brings up a really important point. I'm going to transition over to you for a moment. And that is that why do we care so much about the fact that the sun is doing all this stuff? Yes, it's beautiful. Yes, it's great to learn about, light and energy and heat and how stars act. But more importantly, I have come to realize that in my work, with NOVA and that, and how they've recently done some programs about the sun, that while this activity is not new to our star, our impact on Earth is increasingly important because we are technologically becoming more and more advanced and susceptible to this solar activity.
Oh, we are.
You come into, the work that NASA does comes into play to help figure out and understand how we protect ourselves and all of our satellites and everything from this activity. So
that's right. What's really important about that whole point is the reason that we're studying the sun as intently as we are right now. One of the main reasons is up until a few hundred years ago, most people on Earth didn't really care what was going on in the sun apart from it bringing warmth and heat and light and growing crops and day and night and all those wonderful things the sun does for us. But until technology and electricity and all of these types of things that we rely on now, we didn't really care a whole lot about what happened. Now we do, because not only are satellites and astronauts and people in space and space stations and all of that affected by these coronal mass ejections, but people down here on Earth can be affected as easily as with a blackout. Back in 1989, a sunspot cluster came around and a huge coronal mass ejection occurred. And a few days later, it created this ripple effect through our power grid system in the entire northeastern part of the United States. And the entire power grid went down for several days. And since that event, we've been really careful, and we've been working, the power companies have been working very hard to make sure that this cascading effect doesn't happen again, and that we're less likely to have such a huge blackout. And it was simply caused because the sunspot erupted. We had a lot of electromagnetism a lot of electrical power generated in the magnetic field that surrounds our Earth. And all of that electricity has to go somewhere. And so it looks for places that can conduct it. And it can be the Alaskan pipeline, which corrodes a lot quicker during a storm. It can be any set of power lines. As a matter of fact, I think there was a Harrington event, James Harrington, Harrington event that years ago caused telegraph lines to actually, there was a cascading effect, and some of the telegraph stations and the places where they were tapping out their messages caught fire. And we have to be careful for that.
Wow. Well, and I want to give Troy an opportunity to talk a little bit about the mission that he's working on and how it's evolving and growing this sort of structure of observation that we have of our star, because it's increasingly important. But we have a quick question from Ted, who asked, he's looking at the SunLab page and wants to know how to get to the image that we're looking at a little while ago. So Ted, if you could just let us know, or write another question, tell us which exact image you're looking at, because I'm going to switch over real quick and show you which one I think it was that you were looking at. If you go to today into the SunLab and you enter the research challenge, and that will take you directly into this open investigation section that you can begin, that will get you to the sun today. And what I've done is turned on a few different instruments. Now, here on the side, you can add a couple instruments. I've added, and by instruments, these are particular cameras that are situated on different satellites. So I've opened one instrument that is SDO Observatory, and I've looked at everything here in measurement. These are wavelengths of light. And I've chosen 171 nanometers, which is a very good region of X-ray light that lets you look at these very high energy events. And I've also opened this one here on SDO, which is 304 nanometers, which is, everything's the same except for that. And then the third one I opened is the continuum, which is just the plain white light view of the surface of the sun, and that's where you can really see these sunspots. So by turning these on and off, I can create different views of the sun, and that is right now today. If you want to change the date, you can get to these other ones. So I'm hoping, I just realized that you probably aren't looking at the right screen. There you are, you're looking at Troy. I hope this helped. Let me say this really quickly again. So when you go into the SunLab, this right here is what allows you to add the instrumentation that brings up the different views of the sun that you can turn on and off. And I'm hoping that that helps. And if it doesn't, write another question. And towards the end today, we'll have another chance to spend a little more time in here, okay? Happy to help. So now we're going to go over to Troy and let Troy share a little bit more about the mission he works with and all the different solar infrastructure. And we are going to then move into the educational resources and materials to help you bring this into your classroom, because we have a lot of great resources from NOVA and NASA that can really connect you to some of this real world stuff, and a lot of it has to do with doing authentic research. So Troy, I'm going to start with your presentation and let you take it from here.
And I believe, thank you, Rachel, and I believe you're going to show us a video here in just a second. And if the video ends up being a little bit choppy, don't worry about it, because in the showcase, Rachel kindly placed all the links that I gave her for the videos that we'll be showing you tonight. So if you have any trouble, you, of course, can go and look at that on your own in your browser. So that we're going to open up with, go ahead.
Here we go.
Okay, great. Okay, I'm watching my screen, waiting for it. I'm really into this mission. I've been working for the MMS mission now for about 2.5 years, and I see a screen, but I see a PBS LearningMedia screen, but not a movie quite yet. And there, okay, so wonderfully changing.
Yeah, I went to the wrong browser. It's my fault.
Oh, no
I apologize.
problem. That's great. Yeah, no, I thought I'd say something just in case.
Thank you.
But the MMS, It's a mission that basically is one of the many satellites that's going up to study the sun. And what you're looking at now on your screen is this invisible magnetic field that surrounds the Earth. And that magnetic field, because the Earth is a giant, basically a giant magnet because of its molten core, there's this beautiful force field called the magnetosphere that surrounds us and actually deflects a lot of the plasma that comes from the sun once we have one of these giant eruptions or explosions. But the further out in space you are and the further away you are from Earth, the less protected you are from those kinds of effects. We also have a wonderful atmosphere, as you know, that protects us from many of these effects. What you saw in that video, though, were 4 satellites that I'm going to tell you about a little bit more in just a moment. And those are the MMS spacecraft. There are 4 of them that are 4 separate but identical observatories, which are extraordinary, and we'll be launching those in March, so I'll get you ready for that too. One of the first slides you're going to look at, you'll see a picture of the aurora, and I believe it's slide number 2. And that slide, I don't know how many of you may have seen the aurora, but the aurora, it's a remarkable, beautiful visual representation of a magnetic storm going on around the Earth and in space. And those have been going on, of course, for as long as Earth and the Sun have been here, and we've been here for a long time. And there's a lot of wonderful indigenous knowledge about the aurora that we have materials that we've written about that are available on some of our NASA websites, and I can share those with you a little later. Right now, I'm seeing all of my slides at one time, and I'm wondering if I can see them one at a time.
I had hit play, so.
Okay, we're just waiting on a little bit of a lag there. Okay. Zoom in.
Yeah, I'll do it this way.
Okay, works for me. There you go. There's the aurora. Now, I don't know if in the Google Hangout, if in the chat room, maybe some of you, if you can just let us know with a yes or no, or where you may have seen the aurora, if you were in the northern United States, or maybe Norway, or in different places. But the aurora are extraordinary, and there are places where we love to share images of that. Now, what causes the aurora? And clearly, many people for centuries are asking that question and really came up with a lot of ideas. But in the next slide that you'll see that I have for you, it's a picture that shows you something called a coronal mass ejection. And let's see, and it says coronal mass ejection crossing the Earth's path, but what you're looking at is a disk of the sun. It'd be on that slide, the solar dynamo movie slide, the sun's magnetic field.
This one?
We'll go back just one more. Right there. Now, the reason I'm showing you this is when people look at an image of the sun, often at sunset, they'll just see a round disk, and often kids will think the sun, and you ask them what color is the sun, and they'll say it's red and blue and green and all the colors you see during sunset. And it takes a little bit of time to convince the kids that our sun is actually a white star. And you can actually convince them of that by saying, in the middle of the day, on a clear day, if you go outside with a white piece of paper and the sun is directly overhead, what color is that piece of paper? And they'll say, well, it's white. Well, if the sun were red or blue or green, what color would the paper appear to be? And they would say, well, it would look like all of those different colors. But because the kids are holding a white piece of paper and it's actually reflecting white light, that shows us that the sun is essentially, it's a white star. Now, just to the right side of that image, you see a huge, and right beside that is a little image of Earth, a little blue dot. And that just gives you a little bit of the scale of how small Earth is compared to that sunspot. Yes?
Rachel, I think, Rachel, could you fix the screen to you? So I think right now everybody's seeing Troy.
Oh, is that right? Well, that's too bad.
Yes, screen.
Thank you.
Okay, there we go.
There we go. Here, I'm talking away, and you're looking at the spots on my face instead, right?
Yeah.
The Troy spots. But now I'm seeing Ralph on my big screen, and in the tiny screen I see my slides. But if everybody is seeing the sunspots, we can go on to the next slide, which shows you a coronal mass ejection.
Mm-hmm. You know what? Is this better?
Yeah, now I'm seeing my screen.
Okay, great.
Okay, and if you can scroll up just a little bit, you'll be able to see slide number 4. And it says crossing the Earth's path, and it shows a huge coronal mass ejection image with a little tiny image of Earth. You can see how small Earth is compared to just one huge explosion from the sun. So it's a good thing that we're 93 million miles away from that star, or Earth wouldn't be around for very long, or at least life as we know it wouldn't be here. If you go on to the next slide, which is slide number 5, I wanted to talk a little bit about the sun, the solar cycle. And what's really beautiful about the sun, and we don't have a lot of time to go into this, is that essentially the sun goes through these 11-year cycles. If you look at this image, you'll see back in 1996, in the very top of the image in the left, the sun doesn't look very active. You just see a beautiful undulating red, almost boiling looking sun. And then as you move through the years, up through 98, 99, 2000, and 2001, the sun's magnetic field is winding and twisting over that 4 or 5 years until it finally gets so complex in its magnetic, I like to call confusion, that sunspots and magnetic field lines start to get tangled and knotted up. And everywhere these magnetic field lines get twisted and knotted up, much like twisting a rubber band, if you keep twisting a rubber band, after a while, you'll notice little knots pop out on the side of where you're twisting this rubber band. When these magnetic field lines on the sun get twisted up, because the equator of the sun, being plasma, it's moving a lot quicker than the North and South Pole can. So the poles can't keep up with the rapid rate of the revolution of the sun around the equator. So it wraps up the magnetic field lines, and during a time called solar maximum, which was in 2001 in this picture, the sun's magnetic field lines were just really tangled up, which is normal for the sun, but that's where sunspots start appearing through the corona and through the photosphere of the sun. You start seeing these bright spots and dark spots and all of these explosions and coronal mass ejections and flares. And then the sun begins to unwind. As a matter of fact, its magnetic north and south poles flip in that period of time. The south becomes north and north becomes south. And then as it winds down, it starts to unwind back down to 2006, and it's a calm sun again. And then it starts the whole cycle again. So in 2007, all the way up to just really, we got up to solar maximum just a few years ago, and now we're seeing a lot of these coronal mass ejections and storms happening right now.
Hey, Troy, I know that last time we had a solar maximum a couple years ago, or last year, I guess.
Yeah.
Things weren't acting quite normal, and I remember they were worried. It was quieter than they thought, and now things, they've had a lot of activity. Is over time, has it sort of started to emerge that things are okay again, or
yeah.
Was there a weird cycle this time?
We did have an unusual cycle, and we actually, for a period of time, the sun stayed quiet for a bit longer than we thought it should. And we thought it was going to start winding back up, and then it quietened down just again, which was unusual. But then it wrapped back up and wound back up, and everything started happening normally. And that does happen from time to time. And ever since they've been keeping data on the sun and on sunspot activity, and really trying to keep records of this, we've been noticing an overall effect of the sun. So as the sun back, several years ago, tens and tens of years ago, when the sun goes into a cycle, you'll start seeing this little zigzaggy shape that the sun's solar cycle is going up and down. It's like the magnetic field lines are active, and then they go from maximum to minimum and maximum to minimum. But overall, you'll also see this general shape where these little zigzags go higher and higher and higher. So there's actually a greater cycle that occurs, and we're pretty much on track with that. So even though there are glitches, what seem like glitches from time to time, and some delays, and when we have maximum or minimum, overall, the nature of the sun pretty much stays pretty constant and pretty reliable.
Great. So I'm glad to hear it got back on track. And that's probably good for this part of our system here, which is the society that
sure is
impacted by.
Yeah, it's really important. When you're looking at this particular slide, you see satellites, and you see airplanes, and some antennas, and the Alaskan pipeline, and all of that, radios. All of that's affected dramatically by what the sun is doing, and we have to be ready for that. So what's interesting about our generations, like this past generation and generations to come, is we really do have to get really good at predicting space weather. So not only do we need weather forecasters on Earth to talk about Earth systems that are happening and storms and hurricanes, but we really do need to have space weather forecasters as well. NASA and NOAA both work very hard right now on learning about the sun to try to figure out when storms we can anticipate them happening, when we think that the sun might produce a huge coronal mass ejection or flare that would be in an earthward direction that would affect us. If it's going off in any other direction, unless we have spacecraft or we're out in space somewhere, we're not as worried about that. We're really worried about it, though, if it comes to the Earth. We had a Halloween storm a few years back that was really powerful. I mean, we had a giant coronal mass ejection that really could have done significant damage to a lot of satellites and our communication systems. But it just glanced us, the storm and plasma cloud, the magnetic fields, just glanced the Earth enough to let us know it was there, but it wasn't a direct impact, so we're really, really lucky.
Well, Halloween seems to be a dangerous time for the Earth.
It really does. I'm not sure what that's all about.
I just realized that this time of year, it's a couple years now that this has happened.
That's true. And maybe there's a connection. We should do some research in that to see.
But
what's going on.
the other thing is that the concept of having space weather people. I mean, we see weather people every day telling us, what's going to happen, what to wear. The concept of having a space weather person is probably pretty for, a lot of people don't realize that, we have those people out there who worry about space weather and that there is such a thing. But and that we're increasingly important with all of the satellites and communications that we have up here, so up in space. So that's kind of a really new sort of emerging area for careers potentially.
It really is.
Students need to know about.
Yeah, we have a few programs, and we're working on one right now. I was talking to you, Rachel, about it just yesterday. But it's a program that actually walks kids through how to easily and quickly collect this solar data. And then they can turn that into a type of television weatherman script. And then with right Chroma Key software and any kind of video camera, we were promoting the idea of kids becoming space weather forecasters. And it was a lot of fun because you end up having journalists involved with science, with writing and English and art and graphics, and you can bring a whole cross-disciplinary program together in your school. And it's all about space weather and something that's very relevant to today. The image that you're looking at right now is one of my favorite ones. It's I don't know if it's the geek in me or the helio nerd part of me.
It shows a tremendous investment, I think.
It does.
I mean, we're really up there looking at this, and we are looking at it from all different angles.
We have many, many satellites up there right now, as you can see in that slide, including stereo, SDO, and several others. That are, each one of these satellites can only hold so many instruments, and the scientists get together and try to figure out what's the next thing that we would like to ask and know and learn about the sun. And then they work with engineers and technicians after they've determined what science they're looking for. And these engineers and technicians all come together and they start figuring out ways to create satellites with the right instrumentation to go up and answer these individual little questions on some long-term basis. So every one of those satellites, some of the instruments on them may be similar, but many of them are quite different. And each one of those gives scientists and people on Earth these days a little bit more of the puzzle, the picture, the greater picture of what it is, what's happening with our sun, which is a very average but yet active star, and we live relatively close to it. And so we're having to learn how to live with our star. And one of the things that I think is very interesting about this image, you can see a lot of the solar wind in that image coming off of the sun, plasma, and we have this huge, beautiful magnetic field around the Earth. We actually live within the atmosphere of our star. Most people think the sun is just far, far away and it affects us once in a while. But the sun is also a giant magnet. And I really like to point out that its magnetic field is way bigger than the Earth's magnetic field, of course. As a matter of fact, its magnetic field encompasses the entire solar system. So we live within a magnetic bubble that's created by the sun, which protects us in some ways from intergalactic particles and things that could come in from outside of our solar system.
Is that why there's Andromeda down in the corner?
Oh yeah, look at that. Yeah, I just noticed
Is
that.
that
I don't know
because
if that
of
was
the
just a
sun
position.
protecting us from? I just wondered why. It seems like an interesting choice, but
I
that
think you're
is
right.
probably why.
I actually didn't notice, and actually that would be a very good reason to have that in that image, and that could be why they put that in there. I wouldn't be surprised if Steele didn't put this together, so I'll ask him when I get back to work next week, which will be cool. And you also see Voyager 2 and right underneath the sun, which is cool. It's actually still sending data back. One of the Voyager spacecraft are still sending data back to the Earth, and it just crossed into interstellar space, which is our first spacecraft to do that.
So we're adding 4 more.
Yeah, right there's MMS.
Is it 1 or 4? What would you like to? How do you call it?
It's 4 observatories. It's the MMS mission, but it's made of 4 identical satellites or observatories. Now, what's interesting is each one of those observatories has about 26 instruments on each one. They're all the same. And the reason we have 4 is because what we're trying to do is we wanted to answer a really fundamental question: is what is magnetic reconnection? And what I mean by that, without getting too complicated by it, it's basically anytime you have magnetic field lines, often in space, if you have field lines from the sun being generated by the sun, you have field lines on the Earth being generated, these field lines often come together, and when they touch in space, they often connect and disconnect violently. And just like rubber bands connecting together, melting in the center, and then ripping apart in 2 different directions. And that is actually it's the fastest, most powerful particle accelerator in the known universe when that kind of magnetic reconnection event happens. Now, we're sending 4 satellites up into space in March 12th. They'll be on top of an Atlas V vehicle, and they will fly in a pyramid tetrahedral shape around the Earth like jets for 2 years. And we're going to individually control each satellite with 12 rocket thrusters on each one. And we'll be able to let those satellites in their orbit together move between 10 and 100 kilometers apart. So we're basically making a small pyramid, and we can grow that pyramid with our satellites and then bring it back down to a smaller shape when we want. The whole point of having 4 satellites is because we want to fly them and actually intercept one of those giant magnetic reconnection events. So when those field lines come together like I'm showing you with my arms and they touch, we're going to bring all 4 satellites right around that and snap those instruments all at the same time, and they will capture the data of that magnetic explosion in 3D and send that back down to Earth on its next pass by our signals on Earth, which I think is extraordinary. And we're going to do that for 2 years. So the satellites will keep flying around in orbits through space and anticipating these magnetic reconnection events, capturing the 3D and sending them down to Earth. The picture you see right now, it's a Grand Canyon analogy. That is a picture of the Grand Canyon from space, and that is the reason that's in there is because where these magnetic field lines come together and touch in space, where they explode and connect and all of this stuff happens that we want to know and learn about, is roughly the size of the Grand Canyon. That's how big that explosion or those magnetic reconnective regions are. Now, what I'd like to do, that's the science. Not only do we need scientists to understand the science and tell us or ask the right questions and things that we need to know and piece this puzzle together, but once the science is determined, we have to create the satellites. So we have to look to our technicians, our engineers and technologists to figure out how do we get this equipment that we're creating to the right spot in space to be able to capture the data that these scientists need. And I believe, Rachel, if you can, on YouTube.
We're starting it now.
Perfect. Yep, 3 days and 1 minute. Now this is available on YouTube. We've had about 10,000 views. That's good news. It's increasing. But I actually, for education public outreach with our funding, went out and bought a basic GoPro camera and gave it to one of our official photographer, and she worked with some folks and some people in the Office of Communications, and they placed the GoPro camera up on a tripod inside one of the clean rooms that housed all 4 MMS spacecraft. And over a period of 3 days, they captured images and then brought them together, and now in 3 days and 1 minute, you're going to be able to see all the activity that took place as we stacked those 4 spacecraft in the configuration that they will be on top of the rocket on March 12th. And what's really kind of interesting is just this past week, actually yesterday, when I was at Goddard, they had stacked two of the spacecraft, like you see right there in that image. And they're going to bag it up, get them ready, and ship that down, drive it down to Cape Canaveral to start preparing it for launch. And then within a matter of weeks, they'll stack the other two spacecraft and do the same. In this video, you're watching them stack all four, and that was because they were testing the spacecraft. Of course, we have to see how it's going to operate. And they actually place these spacecraft through a series of rigorous tests. Sometimes they put them in a shaker room and they shake it to simulate launch so that we know nothing will shake off or vibrate or the instruments will be messed up. And if they are, that gives our engineers a little indication. It's like, well, we need to fix that. You know, and that reminds me, Rachel, of some of the design principles that are in the NGSS. Because
the engineering design ones. You're watching the engineering design practices essentially
in real life.
in 1 minute, encompass how you piece together an intricate satellite and send it off to.
It's extraordinary to watch.
And when's the launch coming up?
March 12th. It will be a nighttime launch, so it's going to be beautiful. And what we'll do is, and I'll be sure I'm in touch with you and PBS and NOVA and all the affiliates, because we're going to have a live webcast of that, where we're going to have a camera crew on top of the vehicle assembly building. It's the one that you see at the Cape that has the giant American flag on it, and you see them rolling. In the old days, they'd roll the shuttle out of it.
Yeah, it goes so slow.
It creeps. Right. But we'll be on top of that with some cameras and broadcasting that out. And we'll also be doing some live chats and a variety of different programs like you're doing right now, so that people can be part of it and get their students and kids ready for it.
Great. Well, thank you. We're going to come back at the end, Troy, and ask you a little bit about some of the educational materials NASA has to offer, because we know that you have a sort of robust collection of solar resources for educators, and I want to make sure people understand sort of what those are for them. And I want to go to Ralph now and say, Ralph, give you an opportunity to share some of the really interesting research and real data types of projects that NOVA has through NOVA Labs, where you can, and I showed some of it at the beginning where we connected to the headlines, but there's a lot more that Labs has to offer, and so I hope Ralph can share that with you now.
Nice. Thank you, Rachel. And again, thank you so much for that presentation. So basically, the Sun Lab is really interesting. I think this is sort of indicative of what we've tried to do with most of the labs in the platform. But we really want the labs to be a place where students can engage in inquiry. And you as a teacher can sort of guide them through that process of becoming scientists. So I'm just going to go and show a bit of what I'm talking about with some of these resources. So first, in PBS LearningMedia, and if you haven't signed up yet, you should definitely do so, there's a huge collection of materials that are associated with the lab. So if you go here, you can see there's a NOVA Labs collection, and this is basically a place where you'll find a lot of the videos from the labs, as well as lesson plans and links to additional content that sort of supports the implementation of these labs into your curriculum. So here's the RNA stuff, and if you scroll down here, you can see the NOVA Sun Lab lesson plan, the interactive, and the videos are also here. And with the videos, we also include discussion questions. So when you're thinking about how to sort of use this in the classroom, one of sort of my favorite lesson planning strategies is to sort of use the 5E lesson plan. So the 5E lesson plan basically is structured around 5 key E's, clearly. First one being engage, the second one explore, the third explain, the fourth elaborate, and the fifth evaluate. So with engage, what you try to do in engage is basically create some sort of introduction activity or media resource that poses a question or calls upon prior knowledge. So in this case, one interesting thing you might do is to start off with a story of one of these electromagnetic blackouts. And this is a story that I found on NASA's website about a blackout that happened in Quebec, in Canada, in March 13, 1989. And so you can sort of pose or present this story to students and have them read through it and talk about, what could have caused this and what's the reason why these things happen. So sort of once you sort of set the stage, with this question or with this story, then you can sort of hop into the actual lab itself. And there I definitely recommend doing the activities there. So there are some structured activities with counting sunspots and identifying flares that you can do. But it's a really great way to actually give students a hypothesis or some sort of problem they have to solve, or even have them come up with their own. And maybe you have them sort of look over a target area of the sun and study the behavior and see if there's a connection with the blackouts and the sort of behavior they notice with flares and whatnot happening in the sun. So this is a really great way to get students engaged with this idea of actually playing the role of a scientist. And in this case, they'll actually be using the tools of the science that scientists at NASA use. From there, I would definitely jump to the explanation part. And one way you can do that is with the video quizzes. So there's video quizzes in the lab and that are attached to the videos. And so students can actually watch a video, and as they watch the video, they can add their notes. And one cool thing that we have is there's a feature here called My Lab Report. And My Lab Report allows you to actually track, if students log in and create an account, they can actually track the work that they do in the lab. And this is a great way for you to also make sure that students are doing what they're supposed to. They can actually print out the lab report and turn it into you, and you can actually see the notes they've written, how they performed in each one of the quizzes, things like that. So definitely this is a really good opportunity. During the explain part, it's just sort of where the direct instruction happens, where you actually deliver the content. So in this case, you might teach sunspots, teach solar flares, and talk about magnetic fields. The fourth part would be elaborate. So this is when you sort of give the students an opportunity to apply the content knowledge and skills to the problem. So sort of in a guided practice. And the quizzes are great for this, as well as the discussion questions. And so here's one of the videos. This is also in PBS LearningMedia, but this is about the sun's energy. And here we have teaching tips, but also discussion questions that you can use to sort of evaluate the students' comprehension of that content. And the questions are based off of the videos, and of course you're free to always add more. And one thing too is that if you're interested, these videos are also now available in Spanish as well. But the elaborate part is basically the guided practice. So you're actually testing the knowledge of the students, and then you can sort of finish it up with a formal assessment. That's sort of the evaluate part, where you can either do that in a traditional assessment format, but you can also have students do some sort of project where maybe they collect all the data that they've tracked by doing the open investigation of the Sun Lab, and then create some sort of project or cumulative project that explains their data and presents it to the classroom. So again, the whole idea of this is to really give students the agency to ask questions, but to also explore them. Some additional resources that you will find here, we have a lot of the programs from NOVA also available online. So here you can see the Secrets of the Sun special, which is a really, really great program that covers almost everything you need to know about the sun. There's also the Origins of the Solar System, and this is an interactive. This is actually a video. There's also an interactive that they can do as well. But this is a video that's sort of from the Nova Science Now, which is they're sort of shorter specials. This one's about 15 minutes long, 15 minutes long. Again, really short programs you can sort of plug in into the classroom and have students watch them and sort of discuss them in the class as well. So again, these are just some of the resources, and if you look through here, the PBS collection, you can see each one of the videos comes with a set of questions that you can use, as well as teaching tips. And so again, main idea here is to really provide students an opportunity to sort of take the role of an NASA scientist and to answer the questions that they have, and to be sort of curious about the sun in a way that really engages them in authentic research. So yeah, I think that's pretty much it. But again, those are some of the great resources we have available through the Nova Labs collection that's on PBS LearningMedia, as well as some of the other programs that we have at Nova.
Great. Thank you so much. And again, I just want to say that labs can be used in so many different ways. And in the very beginning, of this hangout, we jumped right from the headlines right into the lab to see what the data is from the sun, from a various range of and what Troy showed you was that image of all of the different satellites that are, you know, together make this amazing network that looks at the sun and monitors it, and we give you access to those data streams and then wrap some curriculum around it if you'd like to use it, or you can use it as a great tool to jump right into looking at the sun. And we have one more collection I'd like to share with you from PBS Learning Media that's sort of central to understanding and being able to speak to the Earth-Sun system as a whole with your students, because so much of what happens on the Earth and in our Earth system science and that is driven by the sun. And we want to make sure that you're aware of this one collection from NOVA called the Earth System Science Collection. And if you go to PBS Learning Media, and just on the very front end of it, I went and I just typed in NOVA Earth and searched for it. It will come up right away, Earth System Science. And PBS Learning Media is a free educational platform that all of the public media programs utilize for distributing their educational resources. And it's free. We hope you will sign up if you're not already. But this collection here offers some beautiful video clips from NOVA's Earth from Space program and some of their other Earth science programs that help you bring some of the visualizations and data. In this case, you could see some gorgeous visualizations of the excuse me, the ocean circulation. And what we're seeing is an era of expansion of our understanding of so many of these big systems of our planet because of these vast networks of satellites that are giving us these new views. And because of that, we're able to create these beautiful short video clips and contextualize them with connections, essays, and other kinds of questions and teaching tips to help you bring the concepts and the videos and media straight from the programs right into your instruction and embedded into your curriculum. And I know that NASA has some beautiful ones too that I'm going to ask Troy, and I'm going to unmute Troy so he's allowed to talk. Troy, you're back. And I'm going to share back to your collection some of the resources that you have to offer from NASA, starting with your wavelength collection.
Yeah, that's right. If you go, this would be great for all of you to do in a separate browser even now. This is so simple. Just nasawavelength.org. And it's a clearinghouse that was just developed by NASA just not that long ago, so many people don't know about this yet. But it has over 2,000 different resources from Earth and space science, including solar activities, magnetism activities, and so on. And what's beautiful about it is, like I believe NOVA also and PBS have their own source of activities, but in the NASA one, these are all the products that have gone through NASA's rigorous product review. And what's really beautiful about it is it allows you to create lists of your own resources that you can save, and then you can share those out with anybody that you want. So if you have an upcoming workshop or a teacher workshop, or you have a group of parents, for instance, that are interested in learning more about what the kids are doing in the classroom, you can create a list just for them and then email it out to them or post it on Facebook or put it on a website, and they'll see the same list of resources. And actually the picture you're looking at is showing a list of resources that one of our colleagues put together. And they're from a school in Pennsylvania, a school district in Pennsylvania. And they didn't want to just stick to NASA resources because there were many others outside of NASA that were wonderful that they wanted to use and had been using. So in the list that you can create NASA Wavelength, you can actually include outside resources of any type that you would like to include. That way you can share it with the people that you need to share that with. So that's called nasawavelength.org, and it's a great place. You just go there, type in anything that you can think of as far as educational resources in the search box, and up pops about probably 15 different ways to find those resources. On
Add again that all of these links are available in the showcase,
that's right,
which is on the right-hand side of the window. We've sort of already selected and linked these to it. So you don't have to write this down in that. It's right there. You should be able to find it and click on it and go to it easily.
Now, the next slide shows a resource that we just developed that instead of going into that resource and telling you all about it, it's incredible, but it's also available on the Magnetospheric Multiscale Mission website. And I believe, Rachel, did we include that link in the showcase?
Yeah, that is there too.
Okay. And that'll take you right to the Education and Public Outreach section of the MMS website. And there you'll find iBooks and transmedia books and resources, videos, and lesson plans for all grade levels, and anything having to do with magnetism, space weather, and everything connected to this particular mission. Now, what makes that collection important is that it's taking resources that you may already have and some resources that are new that we have, and we pull them together to try to place it within a context that you can show the importance of a mission like the MMS mission. You can let your kids know we're studying all of these resources in education in this particular context because we're getting ready to launch a beautiful, wonderful mission that they could all take part in. We're actually working with an organization right now, International Society of Technology and Education, to create a computational thinking series of resources that'll be out next year, hopefully just before launch, and we'll share those with you too. Now, on the MMS website, in the education section, we just uploaded something called card models, and you can actually download, and I don't have a slide of that, but if you're on the website, you'll be able to see a thing called just models, MMS models. Click on that, and you'll see Lego models, paper models, and card models. The card models allow you to create really high-end paper models out of cardstock. And it takes a long time, a lot of patience, and I recommend people who've had modeling experience with paper models do this, but it's a great after-school program for engineering and science. The slide you're looking at right now, I only have this and one other thing to show you. This is called DIY Sun Science App, and this is an app you can get to in iTunes and also, I think, for Droid. And it gives you a series of really quick and easy to do sun activities, and it also opens up a type of helio viewer that you were just looking at, but it comes down to your mobile phone and your smart device, and you can actually look at the sun as it is right now. So I have my phone up. I don't know if you can, if you're seeing me at all, but
I'm going to switch to you.
Okay.
All right.
I have my phone, which is like an.
Well, can you see a sunspot?
You know what? I'm going to find out. So I'm going to click on DIY Sun app, and up pops. Oh, I'm looking at the wrong
There you
thing.
go, wrong one. Oh, it's a little bright. Back up, back up.
Yeah, it doesn't want to show it to you, does it?
It's the lighting. It's dark and light. Sorry.
Well, if when you download this, you'll be able to open up activities, about 15 of them, and then from there you can also open up Show Me the Sun, basically, and it will let you see just like you were showing a second ago. And in that image, thank you so much. In the far right of it, you see the viewer, and what's awesome is you can have your kids doing that in science stations with smart devices or even online as you're going.
So, Troy, as a teacher, when you're doing this, like if you just said, if you have a station set up and you have your students looking at this multi-wavelength view of the sun and that, excuse me, what do you ask them to, I mean, what questions, what can you do with that? What are some of the different ways you use these multi-wavelength views of the sun in this context? Like, can you give us an idea or two? And if anybody out there who's watching has some ideas too, please share them in the chat window or the Q&A window.
One of the programs that we did that was really helpful is we encouraged teachers through a program called Space Weather Action Center, and it's still online. You can actually do a Google search for it, and we can place it in the showcase. But it allows you to download a series of flip charts. And they walk students through in a very introductory way. As a matter of fact, the teacher who uses that program doesn't have to know anything about the sun at all to be able to use this. It's an exploratory activity. So you download one series of flip charts, and it says sunspotters. And you can get a group of kids together. They go through this little flip chart. It tells you what website to go to, where to get the data, and what to look for within just a few minutes. And the kids, within moments, are downloading and looking at data, much like we looked at tonight. But we also have a small, it's not a worksheet, it's a questionnaire that says, did you notice a sunspot? Did you notice that that sunspot changed from when you observed it yesterday? Do you predict that that sunspot will go away, or do you think it will increase in size? Should we alert anybody that there's a possible storm in progress? And what it does, it just gets the kids to start thinking in the ways that our scientists do as they study the same information. And at the end of the Space Weather Action Center program, students go through a series of about 4 flip charts. They get really good at it. They're really fast. And within 10 minutes, they can have a full space weather report written out and ready to report out. They can do it actually every day. And we had a couple schools that got together, and they did, instead of just weather reports over their announcements for the day, they actually had some kids come together and do just like a 30-second space weather report. And it really opened the eyes to a lot of students and parents that we have space weather events around us all the time. Does that help?
Yeah, that's great. I just wanted to ask if, how you as a teacher or educator would use these tools, because I think that's an important, sort of an important takeaway. But so that's the last slide we have to offer from you and all of us, and we wanted to turn it over to people to see if you have any questions or ideas. I'm going to unmute Ralph so he's allowed to talk. And I'm going to stop screen sharing here, and I'm going to see if we can answer a couple of the questions that you guys have. So we asked, somebody asks, let's see, was it Ted here? As a high school teacher, I'm interested in where you guys went to college. Kids are always interested in paths towards current careers. So in 1 minute or so, can you briefly say how you got to where you are now? And I'll start with Ralph.
All right. Yes, so I've always had a fascination with science. So I attended Harvard College. And after that, I really wanted to teach. So I taught for several years in Philadelphia. I taught high school biology and chemistry. After that, I got an opportunity to work at a tech startup company that I co-founded and worked there for 2 years, and really wanted to get back into engaging students and lifelong learners in science education. And so I sort of found my way to WGBH, and I've been here now for almost 6 months now, working on the Nova Labs platform. So yeah, that's my story. Sort of, I've been blending my interest and my experience in science education along with my interest in technology, and it's sort of meets at a really nice nice place here at WGBH, working on Nova.
Great. Wow, that's good. Even though I've been working with you for 6 months, you always learn something new every time. Every time. So, Troy, I know that you have quite a varied path as well to NASA, but do you want to briefly sort of share where you went to school and how you got there?
Sure. Yeah, I was actually well, way back. I was born in Ohio, but we moved to West Virginia right after that, and I ended up going to West Virginia University, where originally I was pursuing a degree in engineering. I wanted to go into aerospace engineering, and didn't know a whole lot about it, and I just knew I was interested in space and aeronautics, and got into a lot of the science and a lot of the math classes that were part of that. And then I realized, I really loved what I was getting into, and I loved the math, but I also missed what I was doing in science. I missed some of the biology, and I missed some of the writing and the art that I was involved in. So I wasn't happy focusing on myself. This was just me on just one career path. So I actually went into education and became a teacher, because it allowed me to stay current and dabble in lots of different fields and be really good at a jack of all trades in a certain way. And I became a professional as a teacher instead. And that ended up being, for me, the right path to go. And right after that, I didn't want to teach in one of the schools in my neighborhood. That wasn't my goal. My goal was, a lot of kids are like this, I think. You want to travel, you want to see things in the world, you want to do things. And education was one of those ways that I knew I could have a consistent income. I knew that I could work with people on an ongoing basis, and parents and families. So actually my first teaching position was on the Navajo Indian Reservation for about 4 years. Then I worked in a Bureau of Indian Affairs school out in the middle of nowhere, and was invited to several ceremonies, and learned a lot about that culture. And right after that, went into Peace Corps and went to Chad, Africa. I was there for a year and a half. And then when I got back to the United States, I started teaching in Virginia at an alternative high school for at-risk kids who were just amazing kids that had struggles of their own. And it was through that experience that I realized I needed to learn how to individualize learning even more than I had in the past. And I got involved in education and technology and decided to get a master's degree at George Washington University in education, technology, and leadership. And that is what opened my eyes up to all the possibilities, like the careers that you're looking at right now. And I put my resume out to NASA, National Geographic, several other really cool places. And NASA called back, and they actually had openings for teachers who did what I did. And that's how it started. So I've been at NASA now for about 14 years.
Great. Well, we're glad Nat Geo didn't call you back because as a competitor. I'm kidding.
I called PBS too, by the way.
Okay, well, we called back. See.
All right. All right.
I'll make mine really brief. I'm also from Ohio, so I don't know, Troy. I born and raised. My background is my degrees in physics and astronomy. I was an astrophysicist. Went to Denison University in Ohio, and accidentally became a teacher. I took 1 year to go. I wanted to change the world. I went to teach high school in the Bronx, sight unseen. I moved to New York City, and loved it so much that I taught there for 5 years, and then moved on to the American Museum of Natural History, where I was able to focus on doing teacher professional development with the New York public school system, still focused mainly on astrophysics and physical science. I then went on to become a planetarium director and a faculty member at the University of Louisville in science education, and I made my way to NOVA and WGBH because I am finishing my PhD right now at Columbia University in science education. And my work focuses on data visualization and media for teaching. So it was a perfect fit. My interest is in learning how to teach in new ways with emerging formats, which basically I believe scientific data in its digital forms, computer simulations, models, all these new things that are emerging are creating new ways to tell stories and teach. And so that's my interest, and that's how I got to be where I'm at now, working with you fine folks. And but I'm still a teacher at heart. I just like to try always finding new ways to teach and ways to help teachers in what they're doing, and with accessibility. I hope that answered the question. I just saw something else popped in. 2 questions. One is, will you be able to access the showcase when the webinar is over? I'm not 100% sure why you can't access it now. I'm hoping that it should be on the side. Is that something that, Ralph, I don't know if you, having used Showcase, would be able to tell somebody where it is?
Yeah, so you should see it on the right. But one thing we can do after the webinar is over, we can link them on the event page for this webinar. So after we're done with this, we can add the link. I think Rachel's created a folder on PBS LearningMedia with a lot of these resources that we talked about, and so we can add that link onto the event page so you can access it after this webinar.
Great. Thank you, Ralph. And Ralph, there's one more question. I'm going to kick it over to you. I'm going to select the question, and we're going to answer it now. Where in all of our resources can students at the middle school level find and gather real-time data that they can then analyze on their own? I know Labs has the capacity to gather data through the HelioViewer tool and analyze it, but I also wanted to see if you had any other ideas, Ralph or Troy, in data gathering and analysis around some of this type of solar data. Right?
Yeah, so I mean the labs platform are created for middle to high school age students. So I mean the open investigation. If you notice, the Sun Lab has an open investigation part in the research challenge, as well as the Cloud Lab and the Energy Lab. And basically, this is provides a sort of an open space where students can sort of conduct their own studies. So I guess in the sense, like, you can't really necessarily export it into a CSV or anything like that, but but there is a capability for students to use those open investigations to answer any of the questions or problems that they're attempting to solve when they're working on a project. But definitely.
I'm sorry, I didn't mean to interrupt. I was going to say, so the data that you would be able to gather with Nova Labs is really the imagery and the movies that you can export out of the Helium store. But beyond that, some sort of numerical data about like flux or wavelength and that, it cannot do that type of information. But maybe that's something Troy can speak to. Is there other sources of solar data that you can point middle school teachers to where their students can maybe gather or analyze solar data?
Yeah, there really is. And I was talking a little bit ago about the Space Weather Action Center. That is actually one of the most incredible resources for teaching kids how to not only see the data but collect it and do something with it, and actually do some computational thinking of their own based on the data that they collect from day to day to day. If we'll put it in the showcase for you so you can get to it. You can do a Google search and just type in NASA Space Weather Action Center for those of you listening right now. And on the home page, and this is actually going to be updated within a matter of months right now, we're working with some different tools that we'll be able to bring in to show and you guys can work with. But what you can do is you can download a teacher's guide that walks you through it. And as you scroll down this page that you're looking at right now, there is a whole list of materials that are free to download that I don't see on that screen. Oh, you clicked on for educators. Yeah, just scroll down to on the home page. There you go. And you'll see flip charts, you'll see data collection sheets, and then the educational guide. But what you would do is download the flip charts, and you would download the data collection sheet that corresponds with that flip chart. And then as the students are going through and collecting and answering questions, the flip chart walks them into several different tools that take them to the data for radio signals, magnetospheric data, aurora images, sunspots, in a real simple, quick way. And then the data collection sheets that you download walk them through the questions that they need to ask to get started. And as the kids are easily and quickly answering those questions, at the very end, they have a complete space weather report they can put together. So the final product is actually a journaling resource.
Great. Well, okay, so I think that was a great answer for everybody. We've got a couple good ideas, concrete. I hope that helps. Jordan, with your question, I'm going to hit done. If not, you could feel free to ask more or another one. So I think that's it for today. We've already held you well over your 1 hour, but this was, everybody who stuck with us throughout this was great. We hope you enjoyed it. I'm going to give you guys excuse me, one last moment if you want to say anything final. But we're also very happy. We'll post our information at the end of this so that it'll live on in this page. This will be archived on YouTube, so you'll be able to revisit it, and we'll share that with you. And if you have any further questions, feel free to reach out to any of us. And we can also post our information on the Google Hangout page. But Ralph, do you want to say anything? And then Troy, you have a moment to say goodbye too.
Okay, great. Yeah, I just wanted to again thank Troy for coming on board and helping us put this together. I think this has been really awesome, and I mean, even I'm sort of sitting here a bit flabbergasted at just the amount of tools and things that NASA is doing to really promote this type of education. So yeah, again, really excited to be here, and definitely the Nova Labs platform is continuing to grow. So if you haven't checked out recently, we launched a lab on cybersecurity. So if any of your students are interested in computer science, that's a really great resource as well to get students interested in those topics. But yeah, I mean, stay tuned. Definitely follow us on Twitter and Facebook, the Nova Labs. We have a lot of new resources coming out, including more educational resources around the labs. So there's sort of an ecosystem that's growing on PBS LearningMedia with videos, discussion questions, and lesson plans. So please definitely follow us and tune in to some of the resources that we're developing. And also, please reach out to us if you have any questions. You can always email us. You can go to Nova Labs website. We have a teacher advisory group, and we basically use this group to communicate with teachers and get your advice and insight on the resource we're developing, and to help us develop new ones as well. So please reach out to us. Thank you.
Thank you. And Troy?
Yeah, I really appreciate the time that I've had here to talk about, especially about this mission. And I really encourage everybody after this to try to stay up with the mission and what we're doing, because we have a lot of resources coming out. We just had a group of students who brought a life-size model of one of the MMS observatories, 11 feet wide, 4 feet high, high detail, that they built in their school in Paw Paw, West Virginia, the second smallest school in the state. And they presented it at Goddard Space Flight Center just last week, and it's on center now for a couple weeks. But one way to see pictures of that and how you can get involved and do similar things or anything greater or smaller than that is to follow us, of course, on our Facebook site. And the last thing I'd like to share with you, and we'll hopefully leave it on the showcase, we have a chat room, and it's a type of listserv chat room, so anybody interested in following the progress of the mission and getting ready for the launch and being part of a launch party or an event, or having your kids tune in to the webcast when we do this in March. It's called Magnetic Space Cafe, so we'll leave the link for you. And it's a brand new thing we just started, so we're growing it. And that's where I will be jumping in, chatting with people all the time, and sharing the latest, greatest. So I hope to see you there.
Great, thank you. And I want to thank Ralph and Troy first for putting the time and effort. This might have been an hour and 15 minutes, but there's a lot more time that went behind the scenes in getting this ready. So thank you both. This was really, like Ralph said, a little overwhelming. And I hope that some of you can go out and catch the rest of the eclipse, or you keep your eye on these sunspots, because sounds like there could be some interesting things happening in the next couple days. And I finally want to thank NASA, especially the NASA Earth Science Division and their educational efforts, who, through their funding, enabled the time and work behind this outreach effort in this webinar. So thank you, for NASA, for your support. We hope to see more of these. We have another one of these next week coming up on October is it the 29th or the 30th? I believe it's October 29th. And it's with NOAA about the upcoming weather and winter climate outlook. So gonna take a little bit of closer look at the weather down here, but it's just as important. So we look forward to seeing you in a week. And good night, everybody. Have a good day. Bye, Troy. Bye, Ralph.
Thanks a lot. Bye, everybody.
Thank you, everyone, for coming.